Okay, then I guess we can. Okay, so here is Alex. He's a researcher at Max Planck. He recently graduated from Stanford University, where he did his PhD, and he's going to be a professor at Georgia Tech. He has done a lot of research in zero-knowledge proofs, in cryptography, etc. And today he's going to talk about zero-knowledge proofs and how we can use them for privacy. So let's welcome Alex.
Great. Yeah, thank you, Stefanos. So I got to say, it was a lot of fun to come out here. My understanding is that this is a class that has like a sort of mixed backgrounds. So we've got some people coming from the economics side. We've got some people coming from the computer science side. Is that right? Okay, well, raise your right hand if you're economics and your left hand if you're from computer science. Maybe some of you neither. Okay, cool. So mix. Great. Okay, so anyways, my goal was to put together a lecture that would make sense, most of the lecture, to everyone. There will be a few slides that are a little bit more computationally involved. I will tell you when that is. But if it's not one of those slides, then this is what I ask of you. So I've been working hard trying to make sure this stuff is all going to be understandable. What I need you to do is to stop me if it's not understandable and to ask questions. So do not hesitate to do that. So the goal for today is for everyone here to learn what the zero-knowledge proof is, what it can do for you, and in particular, what it can do to build blockchain-like systems that have privacy guarantees. So that's what you should get by the end of the day. You should have a sense of what are some privacy-relevant problems that come up in the context of blockchains, but also in other contexts. What is a zero-knowledge proof, and how can it help us solve them? So that's the long-term goal. But I want to start with a quote that I think is very relevant to how blockchains work. And it's also somehow relevant to how zero-knowledge proofs work. So this is from Louis Brandeis, who ended up being a Supreme Court justice in the US. I would say he's probably the second most important Supreme Court justice after John Marshall, who basically created the modern Supreme Court. But before he was a Supreme Court justice, Brandeis was a lawyer who commented on all kinds of things. And this is a quote from one of his essays, What Publicity Can Do. Maybe you've heard this quote before. It's reasonably common. He says that sunlight is said to be the best of disinfectants. So usually I hear this stated, sunlight is the best disinfectant. Well, that's not quite how he wrote it. This is how he wrote it. And I think that this is a great quote to think of in the context of a blockchain, because what is he saying here? He's actually talking about government. He's talking about making government work well. That's what he means by disinfectant, making it work well. And sunlight in his mind is transparency. So what Brandeis is saying here is that one way to build systems that work properly, I would say that have integrity, is to use transparency, to make the operation of the system public. And basically this is how blockchains work, right? So you have a public log, and then on top of a public log, you can build all kinds of interesting systems. So this is exciting. And I do agree with the claim that transparency is a useful tool for building systems that have integrity. But transparency is also an interesting idea, because transparency is the opposite of something that I think is quite important. Transparency is the opposite of privacy. And maybe if we're talking about the operation of our government, we're okay with it being transparent. We think it's appropriate that all governmental actions should be taken in public view. But for individuals, for private individuals, that's something that at least I would say is not good. I don't want all of my financial interactions to be on the internet. I don't want all of my messages to my wife to be on the internet. So when it comes to individuals, privacy is something that's desirable. And the core question that all of today's lecture is about is whether it's possible to build a system that has integrity, in which integrity is guaranteed, but in which privacy is also guaranteed. So in some sense, this lecture is like, hey, what if you weren't trying to use transparency to guarantee integrity? What if you were trying to take a different approach? And the answer is going to be yes. And indeed, zero-knowledge proofs are going to be a fundamental tool that help us do this. So the agenda for today's lecture has 4 parts. First, I'm going to give you some examples of different problems that implicate both privacy and integrity, systems that we would want to build that need both these properties. I'll give you one example from a financial domain, a private payment system. So you can actually think of this problem as being, how do you build Monero, which is a particular cryptocurrency? The second problem that I'll give is a problem from the domain of identity. The problem that I'll talk about is just public key authentication. So how do I authenticate myself to some service, prove that I am who I say I am? And then my understanding is that after this, there are going to be 2 student presentations. I missed who is presenting. You? Okay, great. And in some sense, both the student presentations are on essentially harder versions of these problems. So I'll I guess touch on what you guys are going to be discussing when we get there. So that's what we'll start with, some problems that implicate privacy and integrity. Then we'll talk about zero knowledge proofs, which is going to be a fundamental tool for achieving these 2 goals. I'll give you the definition, and then we'll also see how you can use a proof system, a zero knowledge proof system, to solve these problems, how you can apply the tool to these problems. Then, if you'll forgive me a little bit of advertisement, I'll tell you a bit about my own work, my own research. In particular, I'll tell you about a variation of zero knowledge proofs that I invented called a collaborative zero knowledge proof. And I won't say anything more about it right now, but after we talk about zero knowledge proofs, we'll be able to discuss that in a bit more detail. You can think of this as maybe being a generalization of zero knowledge proof. And that idea of generalization will take us to the last part of the talk, which is where we'll really zoom out. And what I want to do is give you a sense that zero knowledge proofs are a particular tool for obtaining privacy and integrity, but they're only one tool. There are actually a lot of tools that help us obtain privacy and integrity simultaneously. And in the last part, when we zoom out, I'll tell you about some of those other tools that exist in this space. So that's the order of events. Let's get into it. First, the application. So a private payment system. This is our first example problem. So in a payment system, we're going to imagine this as being a balance-based payment system. So all the users, they have accounts and they have a balance in their account. And the thing that we want them to be able to do is to transact. For example, Alice sending $1 to Bob. And we would like our system to be secure. And secure here means 2 things. It means both private and having integrity. So what do we mean by privacy? Well, for this lecture, privacy is going to mean 2 things. It means that only a user should know how much money is in their account balance. And only the participants in a transaction should know how much money is being exchanged in this transaction. So this is very much not how, for example, Bitcoin works. Because in Bitcoin, what our accounts, they're actually these UTXOs. And the amount in a UTXO is, of course, public information. And whenever you do a transaction, all the data about that transaction is also public. So our goal is to change that to make all that information hidden. But simultaneously, we still want to guarantee all the integrity properties that other payment systems guarantee. So money needs to be conserved, account balances all need to be positive, and every transaction has to be authorized by the participants in that transaction. There are actually a few different ways that you could do this there are a few different kinds of authorization you could want. If Alice is sending money to Bob, you might just want Alice to sign off on that. Or you might want both Alice and Bob to sign off on that. Both those choices are reasonable. We're not going to distinguish between them. So those are our goals. I also want to call out one non-goal, one thing that we're not going to try to achieve, which is hiding who is transacting with whom. We are going to hide the amounts, but we're not going to hide the fact that Alice is sending some amount of money to Bob. So hiding the identities of the parties in a transaction, that's also a reasonable goal. And this is the goal for one of the student presentations. So who's talking about Zcash or zero coin? Both. Both. Oh, both. Okay, cool. So yeah, so this is the goal of zero coin. So this is a harder goal. This lecture isn't going to talk about. So how do we get privacy and integrity? Well, it's hard. So let's start with what we know, which is how to just get integrity. And of course, you can do this from a public log. So everybody posts their account balance on the log. Alice has the $8, Bob has the B. If Alice wants to send Delta dollars to Bob, then she'll post a new balance, which is changed by Delta, and Bob will have also post a new balance that's increased by Delta. And they'll also post digital signatures that indicate that they have both authorized this change. So this is standard stuff. This is how, this is one way you can build a cryptocurrency. Obviously, the scheme isn't private because all the data is on the public log, but it does have integrity because everybody can check that the rule, like all the validators can check that the rules are being followed. So the question is how to add privacy. And one option is to use the traditional cryptographic tool, the original cryptographic tool, which is encryption. Instead of having everybody post all their data publicly on this log, you could have them post encryptions, EA and EB, of their balances. So EA is going to be an encryption of Alice's balance under Alice's key. EB will be the same thing for Bob. And Alice and Bob, they'll each have these keys, KA, KB. They'll keep those keys to themselves. Those will not be public. After the transaction happens, the account balances have been changed. So we'll also have Alice and Bob post new encryptions of their new balances and the signatures like they did before. So this is a strawman scheme. It has some problems. We'll call this the encrypted log scheme. And the problems aren't privacy, since all the data is encrypted, privacy is guaranteed now. But from an integrity perspective, that's where we have the problem. Because now that all the data is encrypted, the public can't just, the validators cannot check that the rules of the transaction system are being followed. So to put more of a point on the issue, we might ask ourselves, what stops Bob from giving himself extra money during this transaction? Bob is supposed to post an encryption to his old balance plus delta, but what stops him from adding 2 delta instead, giving himself delta extra happens? And the answer is actually like nothing stops Bob from doing this. Bob can totally do that. This is a problem. In fact, actually, in some provable sense, if you were to learn that how to define security for encryption, the definition of security for encryption is basically the public cannot distinguish between these two things. That's like the very definition. I can't tell what you're encrypting. So this is a real issue. The scheme does not have integrity. And in some sense, this issue fundamentally represents a limit of encryption, which is encryption. It can ensure the privacy of your scheme, but it breaks your ability to do computation over the underlying data. And so what would we actually want to do? How could we fix this scheme up? Well, what we want to do, at least in principle, is somehow have Alice and Bob prove to the public, prove to all the validators that they are following the rules, that their encryptions are to the correct values. So they'd want to somehow prove that all of these conditions from the previous slide hold. And we don't really need to fixate on exactly what these conditions are right now. But what we do need to realize is, okay, they want to prove that all these conditions hold, but they don't want to reveal the underlying data behind these conditions. They don't want to reveal the plain texts. And so this kind of proof that we want, this is what a zero knowledge proof is going to be. It's going to be a proof that some private data satisfies some public conditions without revealing the data itself. So I won't define what a zero knowledge proof is right now, but it should be clear that this is a situation where we would want to prove that private data satisfies a public property. So barring any questions about this example problem, we'll move on to another example that also will give rise to the need for some kind of proof about private data. Seeing no questions, let's proceed. The second example, forget about payments. Now we're talking about authentication. Who uses a YubiKey? Any YubiKeys? Stefanos does? No one else? Have we seen them before? This thing? Keep it on your keychain? No. How many people use two-factor authentication on their phone? Like Duo, Google Authenticator, same thing, just on a phone instead of as a physical device. Yeah. These actually been around for a long time. Like I used to work at a bank, and in those days, these would display like a 6-digit number on them, and you'd have to plug that 6-digit number into your computer. Okay, so anyways, how do these things work? Basically, there's a secret key on this device or on your phone if you're using one of these. And when you want to get into some service to log into a website, a server, that server already has your public key. And the claim is that you have like somehow the public key and the secret key correspond. So there's a one-way function F that maps secret keys to public keys. And what you want to convince the server is that I know the secret key that maps to the public key that you already have on file. I have the unique secret key that makes me that person that I'm claiming to be. And the question is, how do you convince the server that you really do have that secret key? One option, of course, is to send them the secret key. And this works. In fact, if you use like a password, that's basically what a password is in some sense. But this actually is not a very good option for authentication. And why is this a bad idea? Well, if we send this server the secret key, and we are using the same secret key for some other server, some other website, then now in the future, this secret key can be used by the server to impersonate us in interacting with the other site. This is why people say don't reuse your passwords. But one of the advantages of this key-based authentication is that it turns out there's a way to convince them that you know the secret key without sending the secret key to them, without enabling them to impersonate you. So we don't, the way key-based authentication works is that you don't actually send the secret key over. Instead, you send some kind of proof that you know the secret key that corresponds to their public key. And this is going to be another example of a zero knowledge proof. We want to convince the server that we know the right secret key, that our secret key maps to that public key, and we want to do it without revealing what our secret key is. Private data, SK, public property, PK equals F of that private data. And then another note about what we're not trying to do here. We're not trying to be anonymous. The server knows who we are. In some sense, our public key, just like on a blockchain in the system, our public key is our identity. So we're not trying to hide who we are. There are situations where you'd want to authenticate anonymously, prove something about yourself while hiding who you are. And this, I think, should also come up in the student presentation in the form of anonymous credentials. But for this, for my lecture, we'll assume that the server knows the public key. So a second situation where we need zero knowledge proofs. So that's all I've got in terms of our two example problems. Any questions about them? Okay, is that very clear or very unclear? So, so how do we, how do we define public proofs about secret data? Well, that's what we'll talk about now. So this is what a zero knowledge proof is. It's the invention of Goldwasser and Macaulay in '86. This picture is not from 1986. In 1986, they were like in their 20s. This is a more recent picture. So first, let's talk about what we're really trying to do here. So abstracting a bit. The goal is to prove some property about secrets. And so the first thing that we'll do is we'll give a name to that property. We're going to call the property the public property P. And we'll assume that it takes two arguments, public data and secret data. X is going to be the letter we use to represent the public data, W, the secret data. W stands for witness, X doesn't stand for anything at all. So our goal, we have some secret data. Our goal, some secret data W, our goal is to hold that, to prove that P holds for it. And thinking about authentication as our example, in authentication, the secret data was the secret key, the public data was the public key, and the property was that they correspond to each other according to this one-way function. So a little bit more terminology. When we talk about there being secret data, that means some people know the data, other people don't. So we're going to give names to these different parties that respectively know and do not know the data. The person who knows the data, we'll call them the prover. They know W, secret data, they also know the public data. The other party is B, the verifier, who only knows the public data. They don't know W. So thinking back to authentication, the person who knows the secret key, that's the client, that's you, you're trying to log into the website. And the website server, they're the verifier, they don't know the secret key. And what's the goal here? The goal is for the prover, the client, to prove that it knows secret data that satisfies this property, and for the verifier to be convinced or to reject the proof if they're not convinced. In the context of authentication, this accept-reject decision, that turns into a decision about whether to let this person into your website or not. Okay, so that's sort of the syntax, right? We've got two parties. We want to create a proof. We want to verify a proof. What security properties do we want from this kind of system? Well, there's a few goals. The first goal, when the prover knows a secret that satisfies the property, the verifier should accept. They should be convinced. So when you're being honest, the verifier should be convinced. The second property is soundness, which is like kind of like the opposite property. When you don't know a secret that satisfies the property, the verifier should not be convinced. And then the last property is the property that zero knowledge proof systems are named for, the zero knowledge property, which is the privacy property. And what it says is that this proof that you create, it shouldn't reveal any information about the secret beyond the fact that it satisfies the property. So it's you are going to reveal that the property holds. That's the whole goal. But you're not going to reveal anything else. This is what we want from a zero knowledge proof system, informally. So now we'll specify the definition more formally. The first thing is the syntax. So ZKP, it's a kind of computer science. It's like an API. There are different functions, and you give them different inputs. We'll define a ZKP to have three algorithms. The first is a setup algorithm, which isn't too important. The idea is you take the setup algorithm and you give that algorithm the property that you want to write proofs about. So I'm doing authentication. I want a proof about public keys and secret keys. Or I'm writing a proof about transactions, the property of the validity of the transaction. You give that to the setup algorithm. It does some setup and gives you cryptographic parameters, public parameters, that you can then use to run the other two algorithms, which are the important ones, prove and verify. Prove takes the parameters, the public data, the secret data, gives you a proof, which we denote pi. Verify takes the parameters, the public data. It doesn't take the secret data, but it does take the proof. It either accepts or rejects that proof. So the idea is that the prover will run the setup algorithm initially, and then the prover will run the proving algorithm to create the proof. They can send that proof over to the verifier. The verifier will run the verification algorithm, and will either accept or reject based on that. Right? And so now we can state the security properties in terms of the syntax. This will be an informal statement of security properties. If you've got a valid W, it should give a valid pi, where the validity of W means that it satisfies P, satisfies the property, and the validity of pi means it passes verification. Soundness of the dual property, constructing a valid proof should be infeasible, should be hard to do without knowing a secret that satisfies the property. And then lastly, set zero knowledge, which says that this proof pi should reveal no information about W. So far, so good? Yeah. So this stuff, the syntax here is all, plenty formal, but these security properties, this is not how a cryptographer would state these security properties. And so this is where I do want to give you guys a little bit more detail in terms of how do cryptographers formalize things like infeasible and reveals no information. So the next 2 slides will be a little bit more technical. If you get lost, that's okay. You can rejoin us after them. So how do we spell out these security properties? Let's start with completeness. A valid W yields a valid pi. So how do we say that? We say, okay, well, for any property supported by the proof system, for any X and W that satisfy the property, then if you run the setup algorithm, and if you run the proving algorithm, and you take your proof, and you give it to the verification algorithm, that algorithm should output accept with very high probability very close to 1. Why are we talking about probability at all? Because some of these algorithms, set up, prove, verify, they are allowed to be randomized. They're allowed to sample random numbers, and in fact, they do. And it's okay if verification doesn't always work, as long as it works with probability 99.999%, some very high probability. So this is completeness. This should make sense. Seems reasonable. The other property is a little bit weird. The next property we'll try is the soundness condition. And our first attempt, it won't really work, but I'll give you the first attempt. So we want to be able to formalize the idea that a valid proof should be infeasible to build without a valid witness. So here's our first attempt. This is called existential soundness. We say, okay, for any property P and for any public data X, if there is no W that satisfies P in conjunction with X, so no secret exists for this property and for this public data, then for any efficient algorithm P star, you should think of this as an algorithm that creates a proof, but it's not the proving algorithm. It could be malicious. It could be trying to fool you. For any efficient algorithm, the probability that it outputs a proof that passes verification is nearly 0. The probability that you reject the proof is nearly 1. So think about this for a second. We're saying if there is no witness, then no efficient algorithm can find a proof. That seems like a good property. And it's good because it ensures whenever you see a valid proof that a valid witness exists. But I would argue, and others have argued, that this formalization doesn't quite capture this informal idea. And why? What was the idea that we're trying to capture? We're trying to capture the idea that in order to build pi, you need to have W. That was what we were trying to capture. And that's not really what we wrote down. Here we said in order to have pi, W needs to exist, not that you need to know it. And this is a very important distinction because, like, imagine authentication. Stefanos uses my website. He has a secret key. That's great. He knows the secret key, he gets from the website. Somebody else tries to use the website. The secret key for Stefanos exists. He has it. But we don't want other people to be able to build proofs just because he has his secret key. So the missing idea here is this idea of who knows the secret and requiring that it should be the entity that builds the proof that knows the secret. And that's not being captured here. So take 2 on soundness. This is called existential soundness. The stronger notion of soundness that the ZKPs that get used have is called knowledge soundness. And so we'll formalize that now. So okay, again, for any P and for any X, consider an algorithm that builds proofs. We require there to exist another algorithm, a meta algorithm called an extractor. And the idea of the extractor is that you run it on the proof producing algorithm and it gives you a witness. So this extractor, it has access to the algorithm that produces proofs. And we're saying given access to that algorithm that can produce proofs, we can find a witness. And then there's some condition here on probability. So the condition says that the probability that the extractor works, that it outputs W, which satisfies the property, should be very close to the probability that the proof is acceptable. So it's okay if you can't always extract, as long as you can extract 99.9% of the time that the proof is valid. It's a little bit more involved. But this is the way that cryptographers formalize knowledge. We say that P star knows W if there's another algorithm, the extractor, that can extract knowledge of W by interacting, by using P star. So then the last property, the privacy property, zero knowledge, is kind of like the opposite property in some sense. And the way that we formalize it is also through a meta algorithm called a simulator. So here the requirement is that for any P and for any X, there needs to be a simulator such that the simulator also produces, it's an algorithm that produces proofs, but it produces proofs, notice, without knowing the secret data W. And the requirement is that the simulator's output should be indistinguishable from the actual proofs. So here we're saying that proof that you have, like you could have constructed something very similar without knowing the secret. And then this requirement is only enforced when the secret exists and satisfies the property. This is the definition of zero knowledge. The way that one way that you can sort of like get some intuition for this is to think about like zero knowledge interactions in real life. So here's one from my own days as a high schooler. I'd come home from school, my parents would ask me how school was, and what would I say? Fine. And tomorrow I would say fine, and the day after tomorrow I would say fine. In fact, every single time I would say fine, right? It seems like my parents weren't really learning very much from that interaction, right? And why not? If you think about it, they weren't learning very much because they could have predicted what I would say before I said it. And that's kind of what's happening here. The simulator is predicting what the proof looks like without knowing the secret. So therefore, the proof doesn't have any information about the secret. So this is zero knowledge. And this is an end of our sort of descent into more involved parts of crypto. So this is how cryptographers formalize the security properties. But to zoom out, I should also say this is really weird. Like if this makes you uncomfortable, that's normal. In fact, there are actually some cool theoretical things, lower bounds that prove things like you cannot build any proof system that's both knowledge sound and zero knowledge in the standard model. So you need to make some very unusual assumptions to make this possible. So lots of fun theory. But let's put all that theory aside. And zoom out. So, big picture, zero knowledge proof system. It's for showing that a property holds. We call the property P. It has public data X, secret data W. The ZKP, syntactically, it's a library. And it has 3 different algorithms, one for setting up the proof system, one for creating proofs, and one for verifying them. The idea is that one party who knows the secrets runs the proving algorithm. The other party who doesn't runs the verification algorithm. And informally speaking, we want the verifier to accept whenever the prover has the secret. We want the verifier to reject whenever the prover doesn't. And we want this interaction to reveal no information about the secret except for the fact that the property holds. So that's the big picture. Great. Barring questions on zero knowledge proofs, the next thing we'll do is try to apply them to the example problems from the drawing. Okay. So let's do it. So here's authentication. This should ring a bell. We have a client who has a secret key. We have a server with a public key. The claim is that secret key and the public key match according to this one-way function. So okay, mapping this onto a zero knowledge proof system. The secret key, that'll be W. The public key, that'll be X. The property is that PK equals F of SK. So that's what P is. P is that equation. We'll take that property. We'll run the setup procedure on it. That'll give us public parameters. We'll have the prover use those public parameters, run the proving algorithm on their public key and their secret key. They can do this because they know the secret key. That'll give them a proof. They'll send that proof over to the server. The server will run the verification algorithm, feeding in the public key. And that verification algorithm will either accept or will reject. And then based on that, the server will either let the client into the website or they will not. So this is how the syntax of the ZKP maps onto authentication. We can also think about how the different security properties of the ZKP are important in the context of authentication. So first, completeness. That says that valid proofs are accepted. Well, that's important here because that implies that when the client does have the secret key and they do run the proving algorithm, they're admitted to the website. That's good. In authentication, we want to let the right people in. In authentication, we also want to keep the wrong people out. Knowledge soundness is what gives us that. When we see this proof in the passive verification, the knowledge soundness of the ZKP implies that the person who made that proof knows the secret. So that means that that person, they have the secret key, we should be letting them. And then last, zero knowledge. means that this proof doesn't reveal any other information about that secret key. This is what's going to stop the server from impersonating the client in the future. And this is like this whole no impersonation thing is very important, because if you didn't have this, I'd have to use a different secret key for every single website. But because we have this no impersonation property, I can use the same secret key, the same YubiKey, or the same authenticator for all the websites. Good. So this is how you can do authentication using a ZKP. I do, since I'm a cryptographer, I have to note there are other concerns that we're not talking about today that also matter. You know, one thing that you might worry about is man-in-the-middle attacks, or you might worry about replay attacks. Like if I see Stefanos logging into some website, can I then give that same proof in order to log into the same website in the future? These are all very important things. They're solvable, but we're not going to talk about them. Great. So that's our first application. So authentication using a ZKP. Now let's try to do private payments using a ZKP. What you're going to see is there's a bit of a problem. It doesn't quite work. So let's do that. ZKPs for private payments. So recall, we're doing our private payments by encrypting all of the data on our public log. So we've got Alice's encrypted balance before the transaction, Bob's encrypted balance before the transaction, Alice's encrypted balance afterwards, Bob's encrypted balance afterwards, and the proposal was to attach a proof that shows that these encryptions correspond to underlying data that follows all the rules from before. Again, we're not worried about exactly what the rules are, but we need to make sure that we're following them. And we want to do this without revealing the underlying data. And so the idea was, okay, maybe we want some kind of zero knowledge proof. So now we know what a zero knowledge proof is. Let's see if we can use a zero knowledge proof to solve this problem. I'm actually kind of curious if anybody already, it doesn't quite work. And I'm curious if anybody already sees the issue. Okay, so I'm gonna start talking through this slowly, and you stop me when it becomes clear what's wrong. So here's a condition, a property. The property is public. The data underneath the property is not public, but the property is public. So this is the P that we would want to write a proof about. That works. That's good. So okay, so we're going to run setup on the property, and then we're going to have some proving parameters, some public parameters. We're going to want to run the proving algorithm. So we're going to need to take the public data and the secret data and feed those into the proving algorithm to write the proof. So let's imagine that we're doing that. So okay, so we got all the secret data, and the question is, like, who's actually going to run the proving? So who are our parties? Alice and Bob. Alice is sending money. Bob is receiving it. The first question is, what does Alice know? Well, Alice knows some of this information. So Alice knows her balance, and she knows how much money she's sending, and she knows her key. But she doesn't know how much money Bob has, and she doesn't know what Bob's key is. So Alice cannot run the proving algorithm on her own. She doesn't have enough data. And we can also think about this from Bob's perspective. Bob, well, he knows his balance and his key, and he knows how much money he's receiving, but he doesn't know how much money Alice has, and he doesn't know what Alice's key is. So Bob also can't run the proving algorithm. So this is a problem. Right? Essentially, what we're dealing with here is a setting where the secrets are distributed among multiple people. And when the secrets are distributed among multiple people, it's not clear how to use a ZKP, because there's not one person that can run the proving algorithm. One thing, of course, that you could imagine doing is saying, okay, no big deal. We'll have Alice send her secrets to Bob, and then Bob can write the proof for the bulk of them. But then Bob can read all of Alice's data, but now Bob knows Alice's her key. That's not very good. This is actually like a real issue, and there are basically two approaches that you can take to try to get around this problem. The first option is to tweak the way that your system works. So like somehow the way that we set up the system, we're trying to write a proof about both people's secrets at the same time. And that's like, we don't know how to do that. It's a problem. So you could redesign the system so that you don't have to write a proof about two different people's secrets at the same time. And this option is basically what Monero does. So this works. There's some cost to it in terms of privacy, but you can redesign the system to do this. But there's also another option, which is, okay, a zero knowledge proof doesn't apply to distributed secrets, but maybe we can dream up some other kind of cryptographic primitive that does. Great. And that's actually what I'm going to talk about next. So far, halfway through the lecture, in terms of steps, but more than halfway in terms of time. So we've seen some problems that implicate privacy and integrity. We've seen how zero knowledge proofs can help us solve these problems, but aren't always enough. And the next thing I want to talk about is a generalization of zero knowledge proofs called collaborative zero knowledge proofs that apply to the setting of distributed secrets. This is my own research. Like ZKP, like I said, they're the Goldwasser and Macaulay, and they go back to the 80s. Collaborative proofs are like 3 years ago. To maybe make the issue here clearer, let's think about proving properties about secrets. We talked about authentication. That's a situation where one person has a secret. Their secret key, they want to write a proof about it. Great, use a ZKP, problem solved. But there are other situations where the secrets are distributed. Private payments is one example. There are other examples as well. One example that comes up in the cryptocurrency setting is money laundering. So, making statements about money laundering, that's like saying that some entity, Eve or evil, has obtained some illicit funds. Perhaps the funds paid as ransom by Colonial Pipeline. Did you guys hear about this? This was like 4 years ago. It's a US thing, so it might not make its way over here. But there was a gas pipeline operator on the east coast of the US that had ransomware on their system and paid this huge ransom in order to get the hackers to decrypt the data and make the system work again. And then the question becomes, okay, who ended up with all that money? And so you might want to prove that a certain entity has it, but of course, the global transaction graph, like different banks know about different transactions. This is a situation where there's secret data, all the transactions, and they're distributed among different banks, different kinds of financial institutions. Another setting where secret data is distributed is in the healthcare system. So I don't know the state of this in the EU or in the UK, but in the US, it's run by different entities, and they are legally not allowed to share data with each other because like that's your health data. That's very sensitive. And so if a bunch of hospitals want to prove something about how, say, they're charging procedure prices, they want to prove that it's fair, they want to prove that it's desirable, like that's a property of secret data, how much money different people paid for different procedures, really what procedures they had done. That's secret data, it's distributed. So lots of situations where secret data is distributed, and in those situations, a traditional zero knowledge proof, where one party writes a proof about their secrets, the proof is pi, the secrets are W, pi shows some property about W. This doesn't really work because, well, we have multiple parties in the distributed context. So anyways, our definition was basically this. So instead of having one prover, P with the secrets, you're going to have a bunch of different provers. In this picture, there will be 3, P1 through P3. And they'll all have their own secret, W1, W2, W3. And what we want is these provers to interact among themselves, to run some kind of joint protocol that allows them to collaboratively construct a proof pi that now establishes that some joint property P prime holds over their vector of secrets. So this vector, it could be like 2 different people's account balances in a payment system. We're proving that we really did transfer money from my account to yours. It could be a bunch of different hospitals. It could be the different banks. Lots of options. Okay, so this is the syntax. So basically, the generalization here is we're moving from a local proving algorithm run by one party to a distributed proving protocol run by multiple parties. The proof, notice, is still verified. The verifier. In terms of security, this still has to be sound and it has to be complete and it has to hide these secrets W from the verifier. But there's also a new security property that you would want in this distributed context. And this new property is that you want to hide WI. So for example, you want to hide the secret of prover 1 from the other provers. You don't want P2 to learn W1, you don't want P3 to learn W. This extra security requirement captures this idea that in the payments context, you can't have Alice send all of her secrets to Bob. That's not an acceptable solution. And if we don't want that to be an acceptable solution, we need a security requirement that rules it out. And this is exactly that security requirement. Alice can't learn Bob's secret. Great. So this is a collaborative ZKP. And this is like a new security definition, but there are ways that you can achieve this very nicely using existing cryptographic ideas. One way is to essentially generalize a traditional proving algorithm. So I'll give you this sort of like this naive construction that's based on existing ideas for how to do this. Which is, okay, so we start with our proving algorithm for the ZKP. I mentioned that the ZKPs, they provide they're a library. One of the functions in that library is a proving algorithm. You open up the library, you look at the source code for the proving algorithm. You take that source code and you feed that source code into a different kind of crypto system. You give it to this other kind of crypto system, which is called a generic multi-party computation, which is a very weird kind of crypto system. It's kind of like a compiler. What generic multi-party computation does is it takes any function that you want, for example, proving, and it turns that function into a distributed protocol that can be run in a setting where different inputs to the function, say different parts of the secret, W1 and W2, actually come from different parties. And in like a totally generic way, MPC will ensure that this protocol is secure, that each party doesn't learn anything about each other's inputs beyond what they know already. And it will ensure that the protocol also outputs exactly what you would have gotten if you had given all the secrets to one person and just had them run that function on their own. So generic MPC, very powerful, theoretically speaking. And from a theory perspective, like that would be the end of the story. We would all go home and declare victory. But there is a problem with this. And the problem is that this generic multi-party computation is known for being super slow. It's known for producing protocols that are like 1,000 times slower than what you started with. And so this ends up being pretty inefficient. And so one part of the fun research here was trying to figure out a way of doing this such that the distributed protocol was just as fast as the local algorithm. And it turns out that is possible, but I'm not going to bore you guys by going into how you actually achieve that. So that'll be out of scope for today. But I will show you like some of the results. So and talk a bit about what we're doing with collaborative proofs since then. So this is like an experiment that we ran after we designed a dedicated collaborative ZKP proving protocol. The x-axis of this plot is how complicated the property being proved is. And you think of this as like the number of lines of code in the algorithm and that define the property that you're proving. The axis is how long it takes to write proof. This is like a normal ZKP. And naively, this would be very expensive, but if you use this dedicated, we found that it's at most 2 times slower than the local algorithm, which is pretty cool. So anyways, a lot of research has been going on in this area since we did our initial work in it. What I want to skip to, though, is what people are doing with these collaborative ZKPs. So I mentioned some examples in the context of healthcare, building a payment system. Those are all reasonable examples. What people have been doing is actually a little more interesting. So something that one firm, Renegade, is working on is building a private marketplace. So marketplace it's kind of like a payment system, but it's a bit different. In a payment system, I say that I want to give somebody $5. I say I want to give Stefanos $5. Great. In a marketplace, it's different because I don't say who I want to interact with. I just say I have so much of a certain good and I want to sell it. And other people say that they want to buy stuff. And if our prices match, then the transaction happens. So there's a kind of computation in here. And Renegade has built such a private marketplace using these collaborative proofs to prove that it's working correctly. Another interesting application, as this graph suggests, sometimes writing zero-knowledge proofs can take a lot of compute, a lot of time. And what do we do with expensive computations? Well, normally we send them to the cloud, right? But there's a problem. If the data that you're working with is very sensitive, you might not want to send it to the cloud. You might not want to give the cloud your secrets. And so one option is to take your secrets and split them in half and give half of them to one cloud provider and half of them to another cloud provider. And so what other groups, Ezekiel and Vermont, have been looking at is doing this kind of trustless distribution to multiple clouds. And the way that collaborative ZKPs come in is once you've taken your secrets and you split them in half, you've given half of them to each cloud. Now the clouds essentially have to build a collaborative proof. They have to write a proof about both halves of the secrets that you've distributed. So that's collaborative ZKP, and they use this kind of technology. So this can also be sort of a mechanism for secure outsourcing. Okay, so anyways, that's the end of that. So collaborative ZKPs, a generalization of ZKPs to distributed secrets. One example of ways that secure computation can get more complicated than you initially think. And then that takes me to the last thing I want to discuss today, which is really zooming out and thinking about the bigger picture here. So far we've been talking about zero-knowledge proofs and their variants. And the basic idea of a zero-knowledge proof is that you have some secret data X, and perhaps an encryption of X is public, but X is secret. And you want to prove that X satisfies some property. So this is pretty useful. This is how private payments work. This is how anonymous credentials work. But this is just like one way that you might want to securely manipulate that secret. So here, and just to give you a sense, like when when you define a zero knowledge proof, you're making a lot of choices about what secure computation means. There's secret data that's encrypted. That's an assumption. The data is encrypted and that some ciphertext corresponding to it is already public. You're also making an assumption that the thing that you want to do with the data is prove that it satisfies some property. Maybe that's not what you want to do. Maybe you want to run some computation on it. You're also assuming, and we already saw this was an assumption, that one party has the data. What happens if the data is distributed? Well, if a ZKP doesn't work, you need to talk with ZKP. So all of these questions, what do you want to do with the data? And what sets the data public? Is it, that some ciphertext data is public? All those decisions, you could make them in different ways. And if you make them in different ways, you get different definitions. So one example that's also quite common is fully homomorphic encryption, where you say, okay, the data is encrypted, but it's not that I want to prove something about it. Instead, I want somebody who doesn't know the data to be able to do computations over it without decrypting. There'd be somebody to start with encryption of X and get an encryption of F of X for any F that they want without knowing the secret key. This is called homomorphic encryption. And homomorphism is like somehow the math term for when like one function happens to find another function. Oops. Yeah, okay. And so here we're applying a function inside encryption. So there's a function happening inside encryption, homomorphism. That's another kind of secure computation. Yet another type of secure computation we actually ran into already today. It's called multi-party computation, where you're trying to apply a function to secrets that different people have. One person has X, another person has Y. They both know an F of X, Y. And there are many other examples too. So you already heard about collaborative zero knowledge proofs. There are other kinds of secure computation, and the list just goes on. Functional encryption, functional equivalence, witness encryption, private function evaluation, indistinguishability obfuscation, function of secret sharing. Cryptographers of all different kinds of secure computation. And I would say actually like this is a big deal in cryptography. Like roughly, if you go to the big cryptography conference every year, which is confusingly called crypto, that conference, like half the papers are just different kinds of secure computation, more efficient, new definitions of security, et cetera. So it's a big deal. And it's quite exciting in terms of what it might mean for building computer systems that are private and have integrity, because this idea of secure computation is pretty powerful. It's quite different from encryption and signatures, which is what cryptography has traditionally done. In encryption and signatures, basically what you do is you secure data. You encrypt data, you put it in a box so that nobody else can see the data. When you sign data, you stamp that data. That data is really the real data. But secure computation is about securing data in a way that allows you to do stuff with it, that allows you to use it, compute over. And this distinction is pretty important because there are some, seems like the slides are just like going automatically, where you don't really need to do anything with the data. You just move the data around. So if you use Signal or some other kind of messaging application, there I create some data, I write a message, it gets delivered. All the application has to do is move the data in front. No computation happens. But there are lots of applications, of course, that compute on data. Spreadsheets, recommendation systems inside social media. Basically, most computer systems compute over data. And for those, secure computation is exciting because it has the capability of adding security to the computation itself. So that's why I think this is kind of an exciting area to work in. And another sort of interesting challenge that this area creates is this question of how security and computation interact in terms of programmability. So this is something I'll highlight because it's relevant to my research, but also to Stefano's. In all of these examples I gave you, there's some kind of function, right? A property to be proved, a function to be evaluated. Secure computation generally works for any function, so it's programmable. It's generic, kind of like Python is generic. You can use Python, the programming language, to do any kind of computation you want. And secure computations systems are the same way. Most of them are programmable, which means that you can feed in any program you want, and then you get algorithms for securely doing that program. These algorithms, you don't need cryptographic expertise to create them. So there's some kind of like separation of concerns that's trying to come out here. And the natural challenge, of course, that arises is that how do you program these things? It turns out that program interfaces for these systems are very low level. They're very hard to use. I don't know if people here have written code in like assembly. Thumbs up or thumbs down, assembly. Yes, hard to write assembly. This is the same stuff. This is the same way. These programmable crypto systems, they're very much like assembly. And so trying to build a big secure application for them is a bit like trying to like Facebook. In assembly language or in terms, it's very hard. And so in my mind, one of the interesting research questions is to figure out a way of programming these kinds of crypto systems using high-level abstractions, just like we use high-level abstractions like databases and such to program traditional computers. So an interesting area. I also think now is a really exciting time to work on this. And I think it's an exciting time to work on this for two reasons. The first reason is that encryption has become ubiquitous. So one example of this is messaging. These days, basically, all of the major Western messaging applications are end-to-end encrypted. So the most recent one is Facebook Messenger, which became end-to-end encrypted late last year. This was actually due to the work of a bunch of people in the UK. And you know, it's pretty exciting. In my mind, there's some real good news associated with this trend, which is it demonstrates that there is value to privacy. So you know, the story of this is basically once there was a playbook for how to protect messages, for how to use end-to-end encryption on messaging, all of the messaging providers felt like they had to deploy that playbook. Even Facebook, that really doesn't have any interest in doing that, and they felt like they had to do it. But there's also a question that this kind of begs, which is, okay, we're doing such a great job of securing messaging. What else should we be securing? And I would submit that one answer is applications that use data, like payment for studies, and so on. I also think that, so then this takes me to the second trend, which is that these kinds of programmable cryptography, secure computation that I'm telling you about, zero-knowledge proof systems, the theory of this stuff is really old. It goes back to the 1980s. But for decades, these kinds of cryptography were wildly impractical. The term that is used is galactic algorithm, which means it's an algorithm that you can run it in a galaxy in order for the algorithm to finish. So why bother? You know, that's what the stuff used to be. But in the last 10 years, the algorithms for doing this kind of cryptography have gotten much faster. And it's only in the last 10 years that we've seen the first real deployments of computer systems that use programmable cryptography. So one of the big deployment areas is private payment systems. So Monero and Zcash, they only exist because of zero-knowledge proofs. They use zero-knowledge proofs. And as these days, they secure billions of dollars resting on programmable cryptography. If you use iOS or Android on your phone, you also have programmable cryptography on your device. So during COVID, when they were building the exposure notification system to help people figure out if they had been exposed to COVID, they wanted to do statistical computations to figure out how many people are we notifying? Is the system really working? But of course, like this is like really sensitive data. And so they wanted a way of computing those statistics privately. And they did that using programmable cryptography, using a different kind of zero-knowledge proof. So yeah, iOS and Android, they have programmable cryptography in them as well, which is pretty exciting. So anyways, this stuff has become very practical in the last 10 years. And I think that fact has, again, good news and bad news. The good news is that it means that this technology is now efficient enough to be useful in real applications. And to be clear, it's still very slow. There's still problems with it, but there are important applications that are using it today, which is quite encouraging. But there's also some bad news. And the bad news in my mind actually is that this stuff is really hard to use. So Monero, Zcash, the teams that built those are like super experts. They understand payments really deeply, and they understand cryptography really deeply. The people at Apple and Google that did this exposure notification thing, those people also have PhDs in cryptography. They're real experts in it. And finding teams that like know the application really well and that know the cryptography really well simultaneously, that's really hard. It's very hard to put together things like that. And so I think one of the things that we're going to need in order to make more progress in this area is some kind of programming stack that allows us to separate concerns. That makes this stuff easier to use so the application developers can use it without understanding how the cryptography works. So anyways, I think this is an exciting area for research. So that brings me to the end of the lecture. So we talked about 4 things, some example problems that involve privacy and integrity, where you want to prove that secret data has some kind of public property in order to make sure that your system print money, for example. Then we talked about zero-knowledge proofs, which are a classical tool that allow you to prove that secret data has a public property. I gave you the definition of them, and then we looked at how you can apply them to do authentication and how you can almost apply them to do private payments. I also talked about a generalization of zero-knowledge proofs called a collaborative zero-knowledge proof that you can use when the secret information is distributed among multiple parties. This is my own research. And then I told you a bit about the broader landscape of secure computation, many different definitions of what it means to compute securely over data that's private. So thanks very much. It was a pleasure to tell you guys about this. And yeah, we'll leave it here. And I think my understanding is we're going to take a break, and then students are going to present.
Yeah.
And in the meantime, if there are any questions, I'll do my best to answer them.
And so before we go into break, does anybody has any questions? No? So what is like, what kind of problem from what we have seen in the DLT lectures, what kind of problem can we solve with zero knowledge proofs in the blockchain domain? Yeah.
Hospital data.
Hmm?
Hospital data.
Hospital data?
Yeah.
Yeah. For sure. It's one example that Alex discussed. So, but I mean, like in the distributed ledger technologies, right? What is one issue that people might have, and with zero knowledge proofs, we are able to solve.
As one thing about the decentralized potential, the hyperliquid one, that people can see the position of the traders and things like that. So there's one kind of like zero knowledge tool, decentralized potential thing that you can open the position without letting people know your position.
That's an interesting example, actually, and quite relevant nowadays. Do you know Hyperliquid?
I don't know that particular group, but applications like this are things that we'll discuss exactly. So another very related application is this idea of trying to run an auction. So lots of auctions are what are called sealed bid auctions. So when you initially make your bid, you don't want to publicly reveal what that bid is. And that presents a challenge. I want to make a bid and be held to that bid, maybe prove that I can actually come up with money behind the bid, but I also don't want to reveal to you what the bid is. This is like a zero knowledge proof. And I guess you can think of this bid as being a position, I think, as you say, to use your terminology. Yeah.
So interestingly enough, like the problem in the Hyperliquid example is Hyperliquid that we think they have like a public mempool that anybody can actually watch the orders of the trades and what are the liquidation levels for some users, etc. But the Hyperliquid operators obviously can see the data. So although you might be able to trust them that they don't do anything bad with it, or they don't sell the data, that's only trust. And there is nothing that guarantees. And actually, there is a protocol called the ZK Lighter that they use zero proofs to build this, where basically you create proofs and you submit encrypted orders. Any other scenarios that people would want to use zero knowledge proofs? Maybe one of the two next presenters.
Like it would be primarily for like trading and transacting data anonymously. Okay, because the specific application would be like probably having like doing your taxes, submitting your taxes anonymously without like knowing how much actually your work is net.
Or even transacting, right?
Yeah, basic transacting is like.
So another recent use case in the crypto world, in the blockchain world, is having a Visa card that you can spend your cryptocurrency through that Visa. The problem with that is that whenever you do a transaction, anybody can look like how much money you spent. Probably not going to spend it because it always goes to specific contract that's controlled by the entity that has created the Visa card for you. But still, everybody can look like, okay, Stefano spent $10 basic. So with zero knowledge proofs that you can have private payments, actually you can fetch this information.
in your daily life, like you want to buy the secrets of Apple, the sailor says I need your passport, I need your driving license to show your age is whether your age like and at that time you need to send your passport link and on the passport the information like your name, your date of birth is all up there and nationalities and passport number all there. So that will leads to the leakage of your privacy. So they will so that everything on it's like that. And also we will use that mostly in the first section.
Yeah, the credentials thing is a great application. This is actually one of the applications that sort of launched the area of research originally, and it suddenly is very relevant in the UK. Yeah, potentially in the EU as well with the digital identity laws that might come up.